Okay, so one thing I promised we would do is call a C function from Python. So I found actually a very easy way of doing it, just Googling today. I haven't done it on this machine though. So from Python. And this documentation is not that great. All right, so it's not something I would recommend. All right, so let me see if I find. Actually, let's add a keyword. The keyword being Swig. So Swig is a tool that creates interfaces between C and many other languages. All right, so I'm going to start by installing. I need very little stuff. I'm going to start by installing Swig. And unfortunately, for those of you who are using Cygwin, you have to open the installer, right? The user interface installer and install it from there. On Macs is relatively easy because you can just say brew install Swig. And this will update and install the package. What this package is doing is it takes a macro, a file like this, a description file, right, and creates, for whatever language we pick, creates the wrapper, creates a wrapper for our function. So that's what we're going to do. All right, so it's installed. So let's pick, or let's create a file. And I'm going to create a good old factorial function. So we're going to have int fact int n. All right, if n equals 0, we return 1, else we return n times factorial n minus 1. So these would be our function, and what we want to call it is fact.c. Okay. Next, we're going to create, also actually using the editor, or we're going to create a file that has this template. And we're going to declare a module, and we're going to call it fact. And we're going to, I think, declare our function here, right? So remember, we have to provide declarations for all the functions that we use. So we're going to say int fact int. And strangely, we have to do it twice. I think we have to do it twice. And we're going to call this fact.i. So this is sort of a interface file. So now we can do swig, and I'm going to look at the options if there are any. Minus L. All right, so we have an option called minus Python. So let's try this, right? Minus Python. And we have fact.i. And if we look at all the fact functions that we have now, we have a factorial.py here. So this is a factorial wrap. All right. So this becomes our module, right? We're going to import fact, and this is the function that gets imported. So let's open these two files, and this is the wrapper that wraps the C file. So let's open these two files. Why can't I just type? Do I have an option to type? No. So fact wrap fact.py. Okay. So it's a pretty hairy file, right? But this is what is going to be the module. And then it checks the version and so on. So the important thing that happens here is this, right? This load module. This load module loads a dynamic library. Dynamic libraries are files that are very similar to the executables that we've been creating with GCC. So instead of creating the typical executable like this one, right? Remember, this is an executable, this one is an executable, right? We've been generating them from GCC. We're going to create shared libraries, which are pretty much the same thing, right? Just that typically what happens is that an executable starts and then loads the shared library and then starts running. Right, and shared libraries are libraries, right, are common code for multiple executables. So it's a way of factorizing and minimizing the footprint of a program. How do we create one such thing? So we're going to compile only the files. So we're going to say fact .c minus o fact .o. All right, so that's one thing. Then, we didn't look at the fact wrapper. That would be also interesting to look at. Fact wrap. All right, and also this is trying to convert what the technical word is marshal data from Python into C data types and C data types into Python, right? It so happens that the int that you see in C in Python is not represented just as a 64-bit entity. It has some wrapping around it. All right, so let's look where fact is being called. Right, so we're going to create fact.so, that you're going to see in a minute. But here, this is the declaration that we have included in the interface file. It is just copied here. And then let's keep searching. Okay, result. So this is what it is called. Our fact function, right? It is called. And then you see, this is, if you look at how this val1 is obtained, you can see it where it is obtained. Ob0 val1 So it is declared here. Oh, okay. This is where it is assigned. Right? So this object 0 is the Python representation of an integer. This function, you don't have to put this down, right? It's just something that, yeah, you need to understand that there's a conversion from what Python sees as an integer and what C sees as an integer. So this is what happens here, right? From object 0, because we are giving this function its address, right? The address of val1, this function, right, will encode object 0 as a C integer, as a 64-bit integer, right? So then the function is called, we get this arg1, sorry, the function is called here. And we get this result, and this result needs to be converted back into a Python object, which is this guy. And this is what is returned, right? So this marshalling back and forth needs to happen whenever we cross the boundary between languages. All right? And this Swig package does this for us automatically, right? Otherwise, all this code should be written by hand, all right? And the code is actually typically not so complicated, but this tool is trying to take into consideration multiple versions of GCC, multiple versions of Python, and get prepared for all the contingencies. Okay, so we're going to compile this file as well. So fact wrap and fact wrap, and we have to include a library, right? So this is one instance where we deviate from, this is not a system library for GCC. This is not a library that comes predefined, preloaded in GCC. So we have to find it, and I spent some time in finding it, and we're going to find it in USR lib Python 2.7. And unfortunately, we're going to use Python 2.7 instead of Python 3 that we are used for, and I'm going to explain a bit later why. There's a good reason for it. All right, so this is how I add an extra folder to look for such header files. All right, these .h files, they're searched in a variety of places, right? And none of these places, these are the predefined places for GCC. And the place where this file resides is not there. So we have to add one extra folder to the search, and the folder is given here. So that's one thing, right? Oh, it still didn't find it? So I have to say this? Seriously? Okay, let's try local. Python 2.7. That's very strange. That should be there. Okay, there's yet another place where we might find it. System library frameworks, Python framework versions 2. What versions do we have? 2.7. Here, include. Here. Still not. Python 2.7. Okay, finally worked. So we find the file. All right. So strange. I did it for a different Mac, and it was in a different place. All right. And now, what do we have? So one thing that we've seen last time, and we don't typically see, is this .o files, right? These are object files. And we were saying last time that files get compiled into .o files on the fly and then linked together. So now we're choosing to do this separately because we want to pass in a library. And we have to find all these folders. So now we're going to glue together everything. We're going to say gcc minus o, and we're going to generate a shared library. So we're going to say minus shared first. And then we're going to call this underscore fact.so. Why is that? Because this is the naming convention. If my module name is fact.py, my library has to be underscore fact.so. And where is this coming from? Let's go back here, and we're doing import underscore fact. Right, so actually if I say control F.so, oh, it doesn't matter. So the .so is by default. So we're generating this, so it's minus output minus o. We're going to take in fact.o, fact wrap.o, and now we have to pass the Python library. And again, we have to find this somewhere. And probably the place to find it, based on where we found the H file, will be system library frameworks Python framework versions 2.7 lib. So this is where we find it, right? But we also have to say what the library is. So I'm going to say minus L Python. And it worked, right? Now, let's look at what does this mean? It means that inside here in this folder, and we were talking about it last time, but we couldn't experience it because at that time I didn't know exactly what everything was, right? So in here we will have a library called what? libpython.so, right? libpython.what? Oh, .dylib. So dylib is actually the Mac OS dynamic library. libpython.dylib should be. Oh, there's not. Okay, 2.7. Right, so this one exists. So because this is what the library is, we have to specify the library. Whenever we specify a library in GCC, all we have to do is say this. The rest is assumed. The rest, GCC will find it, right? So we're specifying minus L Python, and whatever, minus L is the option, right? This is the library as we pass it in. The naming convention is that we have a name like this. On Linux system is going to be .so. On Windows system is going to be .dll. All right. So now we have a .so function. Python, nevertheless, doesn't like Mac dynamic libraries and likes Linux dynamic libraries. For this reason, we have now if I put an underscore in front, we have a underscore fact.so, right? The one that we have generated here, all right? And this is our library. So now we can do import Python, Python. So the question is, which Python should we start? And actually, it turns out there are quite a few Python systems on this machine, right? There's the Python that I installed with Brew. So this is a command that sort of has has its own system. And I have Python 2, Python 3 there. But there's also a Python that comes pre-installed with every Mac. Right? Macs come pre-installed with Python. So there's a Python 2.7, and it is here, right? So I'm going to use precisely that Python because it is that Python that was used to generate the that Swig has used to generate the wrapper. All right, so I'm going to say bin and Python, and I'm going to make sure it's Python 2. Is there any other Python 2? No, it's all Python 2, so you can just say this. Now we can say import fact, and fact has been imported. And now I can say fact.fact of 10, and we get the result. Okay, so what is fact.fact? Fact.fact is this guy. Okay, so if you want to be absolutely convinced of that, let's personalize it. Let's say printf right, so when we call it that, we want to see this message. Of course, if we do this, we have to include right? Notice that there's no main. And now we have to repeat all the steps. So just to make it very clear, let's repeat all the steps. So we don't need to generate a new wrapper really, but let's generate a new wrapper. So remember, we've written a interface file. So I'm just going to print it here. Right? So we have this file, right, which declares the module name, and this fact is the Python module name, right? So it's a module called fact that has a fact function inside. This is why here we had to type fact. All right, and we just declare it, and strangely we have to declare it twice. I don't quite have a good explanation for this, right? This interface file can be converted by Swig into a wrapper C file. The wrapper C file will be the buffer between Python and our fact, and will take Python encoded objects and convert them into C encoded objects. The int of Python becomes the int of C through this. The result of C then becomes the result of Python and gets printed, right? So we have to convert it and create the wrapper. Then we have to compile two files. All right, so first we compile, it doesn't matter, the order is irrelevant here. The fact file, then we compile the wrapper file. It's not this one, right? This one. Okay? So notice one thing as we do that. This guy, this fact wrap here, among other things, includes a header file specific to the Python library, right? Has its own Python library. And obviously, as we compile this, we have to provide a path to where this library, where this header file can be found. And it so happens on my system that it's here. This folder will vary, but in general, Google will tell you there aren't that many options. Usually There can be 3 or 4, and you can try them all in sequence for your system, and one will be correct. So after we have done this, we have 2 new files, fact.o and factwrap.o, right? These are object files. They get linked by LD, by the LD command, into an executable of sorts, right? That executable, previously we saw it was an executable file that could be immediately launched, right? What we're going to do now is generate a dynamic library which another executable could load and execute from within, right? And that executable is going to be Python itself, right? And what we're generating is a dynamic library. The dynamic library that we're generating has to have a very specific name. All right. So if my module here is fact, this has to be underscore fact, but that's all. Right. So the module name comes between underscore and .so. So this is what we want to generate. -o says output. So -o means the output should be fact.so. What contributes to this file? What are the inputs? Well, we have these 2 object files that we have obtained by compilation, right? And we have this library. But this library does not reside in one of the standard GCC library folders. So we want to add yet another folder for search for libraries. And we do this in this way with -L. -L says, look for my library also here, right? And this happens to be the folder. It's a very hairy and nasty folder, but you Google it, you copy and paste, and we do it. This library, the actual name is libpython version number dot then dilib, right? So we don't have to say the lib, which is specific to all libraries. We don't have to say the version. The system will find the latest available, and we don't have to specify the extension, which is the one typical of a dynamic library for the system at hand, which in this case is a Mac. You might have DLL for Windows and .so for Linux. So we do this, and we obtain this file. Okay, and then this file is loadable in Python. So we have the combination of Python of fact.py plus underscore fact.so. That's our module, Python module that was written in C. So Python import fact Python. You see, if I get the wrong Python, so if I'm running this Python, which I have installed with Brew, then I'm getting one that is incompatible with Swig. Okay, so I have to go to the Python that was used in compiling everything. And I can say import fact, fact.fact. And or let's try 20. And then it's recursive. And 20 is a very large number, so we get overflow. Okay. Now, one interesting thing is because we get overflow, if we wanted to compute, so it's factorial, so every time we enter the function, we're going to print this is our own factorial, right? Would be one interesting thing would be to change the type and make it long-end so that we can return the actual result, right? Because of the overflow, this is the wrong value, right? We cross into the negative numbers. And one interesting thing would be to find out what would be, 15. So 15 is still correct. What would be the limit? 16. So this is probably not correct. I'm not sure. 17. So 16 is still positive. So quite likely to be correct. Is there one digit between these? No. The O goes into the 1. So this is not likely to be correct because um, it's not large enough compared to this one. So it should be at least one extra. So there's definitely 15. Let's see 14. So 14, 15. All right, so this 6. Yeah, this is probably not. Oh no, but it is quite a bit larger, right? So this is likely to be correct. 15 is likely to be correct. So let's try to change int into long int and see that the result will be correct. And by the way, if we had written this factorial function in Python, remember Python has infinite precision, so we wouldn't have this problem. So one very simple thing would be, let me remember if fact 15. There's a factorial math.factorial import math. All right, so we can say from and then factorial of 15. So definitely our result is wrong. Right, factorial of 15 is a lot larger. So 12. Okay, 12 is correct. $13 is already not correct, right? So an int can hold up to factorial 12. So let's increase the size. Let's make it a long int and go through the process again. And so I'm not going to keep printing this, but we're going to say long here. And long here as well. Okay, so now Swig is going to pick up the changes automatically, right? It will convert Python integers into longs in C. We will perform this and go back, and hopefully we're going to have a larger range for our factorials. So go again through all the motions. So now it should be easier. So we do this, though this is not really. Oh, we have to change this one as well, right? So now this becomes long. We made the change everywhere else. So we compile fact.c, we compile fact wrap, we link, and where's Python? This is Python. So let's do it nicely. From fact import fact from math. We want to compare, right? So fact of 13 is this, factorial 13, the same result. So let's try 20. right? So it can go up to 20, and I'm not sure how far, so feel free to try, okay? But this is pretty much how we execute um, C from Python, right? How is this useful? So let's say you have an algorithm that is very involved, right? And potentially with high complexity, right? Then you can go and write that one in C, but the rest of your code can be in Python, right? So you can use Python in a very localized way. Um, do in Python the minimal necessary so that your program stays efficient. Um, all right, smaller functions when written in C, they're easier to debug and test. Right, so then you can write test code to test your function in C before adding it to Python, and then the rest of your code can be in Python. In principle, you can manipulate Python objects in C as you want, right? So that is documented quite well. There's this type, this type called PyObject, right, which is also used in the wrapper, right? So you can look at documentation if you ever need it. Right? And then you're going to have Py strings, Py ints, and so on, right? But you can convert arbitrary objects from Python into C, and they will have some sort of standard encoding. You are going to be able to, take a tuple, find all components, and so on. And I think even our function was manipulating Python objects, right? So, but they're generally quite well documented. So you can pretty much do anything that you would have done in Python, you could do in C if you so wish. My recommendation, however, is always to the C function should always be as simple as possible. So manipulate either integers or longs, right, or doubles or strings. If you have a complicated data structure, right, like for instance a list in Python, convert it into a string of comma-separated values, right? Convert the list of integers, put it into a string separated by commas. Bring it to C, parse the string, and put it into a C array or whatever is native to C. Don't overcomplicate your program and don't manipulate Python objects in C too much, because it will make it harder to debug and harder to test. Okay, so keep those as easy as possible. This also makes it very easy for Python to incorporate any kind of other libraries that have not been written for Python. For instance, one very popular package now is Python Qt. So Qt is a graphics library written for C++ that makes, for Windows and Linux especially, makes very nice professional user interfaces. Right, and it's fully accessible from Python. You don't need to know C at all to use it at full power, right? And that's because this foreign function interface from Python to C exists. Right, so pretty much anything that is ever written in C becomes immediately available to Python just because of this interface. Okay, this is pretty much it about going from Python to C. Any questions? Yeah, any kind of function. So anything that converts, I have never tried, structures, but anything that takes strings or integers or doubles would be converted, no problem. Right? Cool. Anything else you'd like to ask? No? Okay. So this is pretty much it.